that b boundary is x, so you can plug in any number for that b boundary, and then they change this to t, just so those don't match. I'm running out of room, so I'm going to make a note. Don't forget, if they give you an in rate and an out rate, you have to subtract the out rate, right? So if you want a total amount, I'm going to just keep it x, but you could do b if you wanted. You take your initial condition, you add the integral from a to whatever boundary is x of your in rate dt or whatever variable, minus the integral from a to x of your out rate dt. And so if you're using a calculator, you only plug whatever you're going to plug in for x for the top boundary. This stays a variable when you type it in the calculator. Okay, so then we have our second fundamental theorem of calculus, which is if you're taking the derivative of an integral. We know that those are like an inverse relationship. They cancel each other out. So if you notice, you're just left with that original inside function. It doesn't change. So it's like these cancel. So you're just left with whatever the inside function was, but now this only applies if this top boundary is in terms of x, right? If that's a number, then it would just be 0. Right? Because if it's a and b, if they're both numbers, then you're taking the derivative of a number, which is 0. But if it's an x or something in terms of x up here, then those are going to cancel, and you take that x and you replace that variable inside. So that would just, instead of f of t, now it's f of x. So maybe it would help if I give an actual example. Let's say you have the derivative of the integral from 5 to x of 3t squared dt. Well, the derivative and the integral cancel, and you just replace the t with x. So your answer is 3x squared. It basically stays the exact same, you just replace the variable. So if it's not just x, you're using chain rule. So theoretically what you're doing is times the derivative of what you plugged in, that top boundary, but since it's just 1, you didn't write it. Down here, let's say you have, well, let me write the formal one, or let's just do an example. So if you have the derivative of the integral, let's say from pi to x cubed of cosine t dt, how would you do that? Well, we know the derivative and the integral cancel, so we're going to take this top boundary. We don't care about what that number is. Plug it in for t. So that's going to be cosine of x cubed times the derivative of what you plugged in, which is 3x squared. And that would be the answer. And the last two are two formulas we've learned. The mean value theorem for integrals. We learned it and then we never used it because it's in your curriculum, but it just never comes up. So I would not worry about that, especially with your shortened test. But it's there if you needed it. That it's just if f is continuous, it's guaranteed that there's some c where this is true. And then the average value is what we use a lot more, right? If it asks for average value of something, you do 1 over b minus a times the integral of that function. So normally when you integrate, you change units, right? If you integrate gallons per minute, then this would give you gallons. But if you do this, if it has 1 over b minus a, the units don't change. So if f of x was gallons per minute, then this would give you the average gallons per minute. If f of x was gallons, this would give you the average gallons for that interval from a to b. This is not the same as average rate of change. Now they derive from each other, but if it asks for average rate of change, that's changing units. That's going up a level. But if it's this, you're staying on the same level, you're not changing units. So just keep in mind there's average rate of change, which is f of b minus f of a over b minus a, and there's average value, which is this. Okay, and I think that covers the main topics from chapter 4. Now obviously there's a lot more and practice and examples, but the main idea was the indefinite versus definite, how to do the area, whether it's geometry or estimating using Riemann sum, and then these theorems. So as you're working through these, let me know if you need help with anything.